Okay, so let's move on to the next topic, which is conjugate symmetric and conjugate anti-symmetric parts of a signal. Okay, so what does it tell? So what happens is that in general, any complex signal need not be either conjugate symmetric or conjugate anti-symmetric. So it can be neither CS nor CAS. But what happens is that so we can split the continuous time signal x of t into conjugate symmetric and conjugate anti-symmetric parts, just like as we have done in even and odd parts of a signal. Okay, so for continuous time case, and we can split the signal x of t in continuous time case in terms of xcs of t plus xcas of t, and same is the case for discrete time. We can split our signal x of n as xcs of n plus xcas of n. So here xcas of t stands for conjugate symmetric part of signal x of t, and xcas of t stands for conjugate anti-symmetric parts of the signal. So same is the case for discrete time case. Okay, so what is that we have to do? What is that we can do? We can split any complex signal x of t in terms of conjugate symmetric part plus conjugate anti-symmetric part. So as the name itself suggests, xcs of t is conjugate symmetric part, so it should satisfy conjugate symmetry property. So what do I mean by that? Xcs star of minus t should be equal to xcs of t, and similarly xcas of star of minus t should be equal to minus xcas of t. Why? Because xcs of t is what? Conjugate anti-symmetric part. So definitely conjugate anti-symmetry means what? It has to satisfy this property. So now let us try to derive the equations for these two cases. Okay, so what is that? We have got xcs star. I write from the beginning. So what is that we have done? We have split our signal x of t as what? xcs of t plus xcas of t. Okay, and what is that we know? We know that xcs star of minus t equal to xcs of t, and we also know that xcas star of minus t is equal to xcas of t, and we have a negative sign here. Okay, so now what is that we do in this equation? Okay, so in this equation we replace t with minus t. So what do you get? X of minus t would be equal to xcs of t, xcs of minus t plus xcas of minus t. Now if you take conjugation, what happens? X of minus t star would be equal to xcs star of minus t plus xcas star of minus t. Okay, but we know that xcs star of minus t is how much? Xcs of t, and xcs star of minus t would be equal to minus xcas of t. Okay, so now what we do, we add these two functions. Okay, which one? The ticked function. So x of t plus x star of minus t. So what will happen? So that should be equal to how much here? So we get xcs of t plus xcas of t, that is x of t. And what is x star of minus t? So that is nothing but xcs of t minus xcas of t. So because we are adding, so these two fellows will get cancelled, and you get finally this to be equal to 2 times xcs of t. So from this we see that xcs of t is equal to x of t plus x star of minus t whole divided by 2. So in that way we can derive the equation for conjugate symmetric part of the signal. So in a similar fashion, if you subtract, you get the conjugate anti-symmetric part. Okay, so what happens to the final result? We can see that conjugate symmetric part of the signal x of t is nothing but x of t plus x star of minus t by 2, and conjugate antisymmetric part is x of t minus x star of minus t by 2, and same rule applies for discrete time case. Okay, next we will take few examples here. So we have the signal x of t to be equal to e power a times a plus jb times t, and we want to find the conjugate symmetric and conjugate anti-symmetric parts. So we already have x of t, so what do we want? We want x of minus t, or yeah, so x of minus t would be equal to, or before we go into that, we can write this as e power a t times e power j bt. So just for convenience, we will split this exponential term. So x of minus t would be equal to e power minus at times e power minus jbt, and to find the conjugate symmetric part we should take conjugation of this. So x star of minus t would be equal to, so e power minus at would be as it is multiplied with e power minus jbt's conjugation would be e power plus jbt. Okay, right. Now to find the conjugate symmetric part of the signal xcs of t, we have to take x of t plus x star of minus t whole divided by 2. So that turns out to be x of t is how much here? E power at times e power j bt, plus x star of minus t would be e power minus at times e power jbt whole divided by 2. So from this we get x cs of t to be equal to, we can take e power jbt common, so whole divided by 2, we can keep it out, so you get e power at plus e power minus at. So that turns out to be the conjugate symmetric part. So similarly, what is conjugate anti-symmetric part of t? So that is nothing but x of t minus x star of minus t whole divided by 2. So after substituting, you get e power at times e power jbt minus e power minus at times e power jbt whole divided by 2, and again what happens, e power jbt whole divided by 2 is common, and you get e power at minus e power minus at as the conjugate anti-symmetric part. So for a given signal, in this way we can find out the conjugate symmetric and conjugate anti-symmetric part of a signal. Okay, so as a last problem we will take an example for discrete time case. So we have x of n to be 2 times e power 3j whole power n, and we want to find the conjugate symmetric part and conjugate anti-symmetric part of this signal. So before we proceed, so let us write down this function as 2 power n times e power j 3n. So just for making our life simple. So again, to find the conjugate symmetric part, we need x star of minus n. So but first let us write down what is x of minus n. So wherever there is n, we have to replace with minus n. So we'll get 2 power minus n, 3 power e power, sorry, so multiplied with e power minus j 3n, that is first one, and we want x star of minus n. So that turns out to be how much? Take the conjugation, so you'll get 2 power minus n conjugation is 2 power minus n itself, but this fellow will become e power j 3n. So now we can find out conjugate symmetric part as x cs of n as x of n plus x star of minus n all divided by 2. So that turns out to be how much? So 2 power n e power j 3n plus x star of minus n is how much? 2 power minus n times e power j 3n whole divided by 2. So from this we see that x cs of n is nothing but e power j 3n is common, whole divided by 2, we can take it common, so you get 2 power n plus 2 power minus n. Okay, so similarly x cas of n is nothing but how much? X of n minus x star of minus n whole divided by 2, and by direct substitution you get 2 power n times e power j 3n minus 2 power minus n times e power j 3n whole divided by 2. So that simplifies to how much? So e power j 3n by 2 is common and you get 2 power n minus 2 power minus n. So in this way we can evaluate conjugate symmetric and conjugate antisymmetric parts of a signal. So with that we conclude this uh, classification of signal, which is conjugate symmetric and conjugate antisymmetric signals, and also conjugate symmetric and conjugate antisymmetric parts of a signal. So next classification we will see in the next video. Thank you.